Good morning, everyone, once again. So let me give you a bit of a background as to why we are having this course. First of all, I think there are more people who have registered. They'll keep trickling in. So we're going to build up over here. As you know, in October 2027, we will be hosting a conference called the International Congress on the Chemistry of Cement. This is a very prestigious conference. It's happening for the second time in India. Apart from England, India is the only country where this has happened. This is going to happen twice. It's known as the Olympics of the cement world. Now, one of the reasons why we wanted to have this conference in India was because we realized that there was a gap in the kind of research that was happening in the area of cement chemistry with respect to the rest of the world. You can see that in terms of the number of articles that are published from India on the subject. There are a huge number of researchers who are working on this subject. India is the second largest cement producer in the world. So obviously there's a need to do research. A lot of people are doing that research, but somehow that research is not reaching the international stage, is not getting the visibility that it deserves. So we decided that we will use this occasion of hosting this conference to also try to build a network of people in India that are going to work with each other to help each other grow, develop, reach the international arena. One part of that is training, sharing our knowledge that we have. None of us can claim to know everything or even a small percentage of what is there to know. So if all of us come here and share whatever we know, whatever little we know, we may be able to transfer some more knowledge to, especially the future generation. And the second part is to train our people to present the way it is expected to, in the way the presentations are expected to be there at international forums like the ICCC that is going to be there in 2027. My hope is to have 100 good presentations from India at ICCC 2027 and to show to the world that within a short span we can go from not having so many publications in this conference or in international publications to a much higher level. So the idea is to bring out the latent talent that's hidden in India. That's what the idea is. And we'll all try to share whatever little we know on the subject with the people who are joining us here. Tomorrow we will have what we are calling the Stakeholder Symposium. It's nice to give fancy names to events, but the idea there is that students, young researchers, will be making 5-minute presentations, and I'll talk a bit more about it towards the end today to tell you what is needed to be done for tomorrow, hoping that a lot of you who are going to present tomorrow are present here today. This is what I'm going to talk about. You see in the schedule there are 2 presentations from me. The first one about production of cement, the other one about hydration of cement. They kind of link to each other, so I'm going to combine them into a single talk. First of all, why are we talking about cement at all? Like I said, India is the second largest producer of cement in the world. We are the second largest, but we are way behind China in the amount of production of cement that happens. We are way behind even many other developing countries in the per capita consumption of cement. China used to produce 8 times the cement that India did, even though our populations were similar. Today, the production of cement in China is dropping. In around 15 years, it is expected that India will be the largest producer of cement in the world. And if we don't do this research right now, if we don't make our materials efficient in terms of resource utilization, cost, environmental impact, then it will be too late. Because by that time, the industry would have peaked. We have to do this right now, because a huge part of the industry that is to be developed is going to be developed in this in this coming decade. So that research has to be done right now. So this is where we are going to start. with the production of cement and the hydration of cement. First, talking about the production of cement. So what is cement? What's the meaning of cement? Let's start the day with a quiz. What's the meaning of cement? Glue? Hold something together? So what is cement? Cement is the binder that's used in concrete. It's the material that is holding everything else together. What everything else? The sand, the aggregates, even the cement particles themselves. This is what is holding everything together. These are particles that may be as fine as a few hundred nanometers to as coarse as a few hundred micrometers, but most of these particles are usually in the range, usually below 50 micrometers in size. Depending on where you are, the particle size distribution of the cements may be different. There are many different types of cements that are there. There are Portland cements. There is something known as high alumina cement or calcium aluminate cement. Calcium sulfoaluminate cements. There are magnesium cements that are being developed right now. Blended cements are there. But today we are going to talk mainly about Portland cement, and we will also talk a little bit about alkali activated materials. So Professor Subramaniam will introduce that later. I'm not going to even try to pretend to understand that I know anything about that. Blended cements, after me there will be talks that cover pozzolanic materials. Professor Piyush Chonsali will talk about that. We'll also end our today's program with a little bit of modeling to try to show you that cement is not just about working in the lab or working in the field, but it can also be working on your computers or even big workstations to carry out your research. But today in this talk, I'm going to talk mainly about Portland cement. Portland cement is the most commonly used cement, and well, I should change the slide. Ordinary Portland cement is not really the most commonly used cement in the world anymore. It's the ordinary Portland cement clinker that's the most commonly used clinker. What is clinker? I'll come to that in a minute. And it is usually blended with other materials. But I'm going to talk about OPC in this talk. OPC, or Portland cement, this was a marketing gimmick, giving it the name Portland. Because the cement that they produced, it gave if you finish the floors with it, it gave a feel of this Portland stone that used to be used. In India, we use a Kota stone. At least in North India, we use it very commonly. So there they were using this Portland stone. It kind of gave that idea. And there was this guy, Joseph Asden, who invented this material that would give a very nice gray, beautiful gray feel, right? We all know that this gray color is beautiful. Yes? No? You don't like the gray color? None of you was excited when I said the beautiful gray color. It was actually his son, William, who came up with a formula that's much closer to the cement that we use today. Last year, people celebrated the 200th anniversary of Portland cement. Portland cement is the way it is because that's how things are there in nature. It's not by accident that what was invented in England, or what some people claim France, England and France never agree on anything. So they don't agree on who invented it, but most people say it's England. So it's not by accident that something that was invented in England ended up being used all around the world. And the reason for that is it very closely mimics the composition of the Earth's crust. What will you find on the Earth's crust? The most common element that you'll find in the Earth's crust is oxygen. Oxygen is there in Portland cement clinker. Silicon, that is there. Calcium is also another major element that's in Portland cement clinker. Calcium has a bigger proportion in cement than it does on the Earth's crust. But then a lot of calcium is available on the Earth's crust as well. If it wasn't, we wouldn't be able to grow. Our bones wouldn't be able to grow. There's a lot of calcium around. And that's why cement is, the type of cement that we use today is very widely used because it's so easily available. People moved away from other materials like lime. In India, we used to use a lot of lime surkhi due to many reasons. It could be resource reasons, it could be environmental reasons, it could be cost reasons, it could be speed of construction reasons because of which people moved away from it. But then this is a material that can be very easily produced with the raw materials that are available locally. in many places. This is what it mainly contains: calcium, not silica, sorry, silicon, iron, aluminium, sulfates are added to the cement. So how do you make this cement? So what you do is you dig out earth. You dig out raw materials from the earth. You take them to a plant in a truck like that. These are pictures I've taken from various plants in India. I don't remember which ones, probably in Rajasthan. Can we switch off this light? Can we switch off this light that's directly on this? Hi. Yeah. Thank you. Even I was not able to see what they were. It was on the slide. So, you dig out earth, you put it in a truck or a conveyor belt or whatever. If you're very fancy on a helicopter, though you can't do that because we're talking about tons and tons of material, and you take it to your plant. All of this material is then homogenized at a certain location. It's taken to the plant, homogenized, mixed. It's stored in stacks, huge stacks, where materials of different composition are there, and then there are reclaimers that reclaim the raw materials from there based on their composition, so that you get roughly the same composition all the time that you're feeding into your cement plant. You want the same composition because you would like to produce a consistent product over time. People would not like it if the same mix design in concrete gives you one strength today and a completely different strength the other day. You would like the material to be fairly consistent. What are these raw materials that we dig out from the earth? We dig out limestone because that contains calcium. We dig out clays because they contain silicon and aluminium in them. These are aluminosilicates. Sometimes you need to add a bit of iron and you get some laterites. For example, you mix them all together, and there are some other things you might also want to add depending on whether you have the right amount of alkalinity or not. Some people have to add feldspar. In India, we are very fortunate. We are very fortunate because the raw materials, the minerals that are there in the earth's crust are so mixed up. We have such a small supply of very pure minerals that essentially you can dig out whatever is in the earth and just put it in the cement kiln, and it contains everything that you need most of the times. Well, sometimes you need a bit of laterite, sometimes you need a little bit of something, but then the raw materials are so mixed that you can, most of the cases, just put that in the cement plant and use it directly just by homogenizing it over time. These things are mixed up, and after they're mixed up, they may be stored separately, they may be mixed up, they may be crushed, and after crushing, they go into this huge tube that is called a rotary kiln. Now, a long time ago, what used to happen was that all these raw materials, as you saw over here, this picture is from Portland Cement Association in US, where they're unfortunate. They have very pure minerals, so they have to store them separately. They have a limestone, they have a separate sand that they mix together, and all these things. So what they used to do was mix them all together using a wet process in a liquid. And when you mix them all together in a liquid, you have to put it in a much longer tube because it takes a lot of energy to dry out the water. To homogenize it, they used to use what is called a wet process. But today, most of the plants use a dry process where everything is mixed up in a dry state, so that you do not have to remove the water afterwards. The amount of energy required to remove water is huge. So there was an oil crisis that happened 80s or something, 70s, 80s. Around that time, most of the cement plants started to switch to the dry process to save energy. So in this tube, all this material is fed at the top. This is a tube in which there's a temperature gradient. There's a burner over there at this end. Over there, the temperature is around 1400, 1500 degrees centigrade, depending on how you've optimized your kiln. And here, you've got this, the temperature over here is usually around 900 degrees centigrade. The material is usually fed into these preheaters or pre-calciners. These are cyclones. The material is kind of crushed into fine powder, put it to these cyclones. It stays for a few seconds in each of these cyclones, passes through each of these stages in the cyclone. Most of the calcium is calcined. And what is that calcination? I'll talk about in a few minutes. And then by the time it reaches here, the temperature is already 900 degrees centigrade. And then it passes through this kiln over here where everything is churned and turned. All of the things interact with each other. They melt, they fuse, they react with each other and produce what is known as clinker. And that clinker is stored in what is known as a CSP or a clinker stockpile at the end. This is what it looks like inside the kiln. It almost looks like molten lava flowing around. This is what a kiln looks like. It's really hot inside. It also feels hot outside, but there's a layer of insulating material that prevents heat loss. The cement plants today are very efficient compared to the ones earlier. They're very close to the thermodynamic efficiency. I'll talk about what that thermodynamic efficiency is afterwards. But do you know why we are having to heat this cement or heat this material to such a high temperature inside this kiln? Why do we have to produce cement at 1400 or 1500 degrees centigrade? You've attended my class. You're not allowed to answer this question. Yeah? Why can't we just use something that can be produced at a low temperature? Yes. Good. Very nice. Okay. Let's not even go there right now. Do you know of any material that's available in nature that reacts with water? Any material available in nature reacts with water? No? Why not? Lime is not available in nature. Limestone is. I'm not saying dissolve, reacts. There isn't, because if it could react with water, it would have reacted by now. It has had millions of years to have the reaction. It would have reacted with water by now. Everything exists in their lowest energy state. So there's a bit of chemistry involved over here. This conference is about chemistry. But a lot of people who work on cement and concrete are civil engineers. And the favorite subject of civil engineers in school was always chemistry, right? Any civil engineers here in the room? How many of you had chemistry as your favorite subject in school? Oh, there are a couple. Okay, the world is changing. But I don't know, I used to barely pass in chemistry. So what we've done is we've created a pseudo-chemistry for ourselves, as you'll see. Chemistry which is chemistry but not really chemistry, and we even use terms that the chemists won't understand so that they're not able to catch our mistakes. Any chemists in the room? Oh, I'm very sorry, you'll have to bear with us through the entire day today. So everything wants to be at its lowest energy state. We want our cement to be able to react with water. And to be able to react with water, you have to produce something that has a very high energy, initial energy. And that very high energy that is needed can only be produced by putting in that energy into the cement. How do you put that energy? You put that energy into the cement in the form of thermal energy. You treat the cement to a very high temperature of 1400 or 1500 degrees centigrade, and that gives you a material with high energy, which is why when you buy a bag of cement in the market, it's very hot. Right? No? The bag of cement is at 1400 degrees centigrade. No? Then what's the use? I put all that energy into the cement, and by the time it reaches the market, all the energy is gone. Okay. So the temperature is gone now. So what happened to all the energy? It's all wasted, right? At the moment I put it in the clinker stockpile, all that, it goes through a cooler after that, and in that cooler, all the energy is gone. So are we doing all of this so that we can run a waste heat recovery system or to make a reactive clinker? Where did all the energy go? Is heat the only form of energy? Chemical energy. The energy is converted into chemical energy and is stored inside the cement. All right? I'm sorry. That's right. Yeah. The energy is stored inside the cement. And why is it stored inside the cement? What's the point of doing that? We'll talk about that in a few minutes. So remember, now we produce a material that has a lot of energy inside it, stored in the form of chemical energy. The reason why we are heating it to a high temperature is because we are producing materials that have a very high enthalpy. All right. Now, all of this material is taken out and then it is mixed with gypsum. Why do we mix with gypsum? I'll talk about that in a minute. You mix with the gypsum, you grind it together. There are various ways of grinding that are available today. Here you see a ball mill where there's another rotating drum inside which you've got steel balls and cylinders that crush the cement to a certain size that you want, homogenize it with the gypsum, and then it produces what is known as ordinary Portland cement. So, where did my picture of clinker go? I thought I had a picture of clinker over there, but my slides got moved around a bit, I think. But anyway, so you produce, after that clinker is crushed with gypsum, you produce what is known as cement. And then after that, that cement is put in bags. Here, a picture from the JK cement plant in Nimbahera, where they're bagging a cement. This wasn't LC3 on that day. And then it being loaded onto a truck. You know, most of the cement in India is sold in bags and it gets transported in trucks. But there's a lot of cement that also gets loaded in bulkers, in bulk trucks, in bulk cement trucks. So there's another one. This is also from the JK cement plant, but I don't know why there was another brand truck standing over there. This is a picture from Fiji, where there was the cement that was just ground over there and was being transported in a shipping container to another island called Tuvalu. Tuvalu is the least visited country in the world. It's one of the first countries that will disappear due to global warming. And this cement was being transported to Tuvalu to build barriers to prevent water from getting in. But you can see it can get transported whichever way you want, in bags, in trucks, and that's the amazing part about cement. You can seal it in a bag, take it over a long distance, but usually you transport it over a shorter distance of a few hundred kilometers. So what happens in this kiln? What are the reactions that are happening? One of the first reactions that happens is your calcium carbonate gets calcined. That means the calcium carbonate gets converted at a temperature of around 800 degrees centigrade. It gets converted to lime and carbon dioxide is released. This carbon dioxide makes the majority of CO2 that is emitted from cement production. But today is not about only about CO2 emissions. We will not talk about that. Materials like clay start to decompose. They give you iron separately. They give you silicon separately. They give you alumina or other alumina phases. They start to melt. And at different temperatures, different reactions happen. I don't intend to read all of that out. But what happens is, as you keep heating, new materials keep forming. There's something called C2S. What is the C2S? This sounds like carbon, sulfur mixed together. Sounds very explosive. It isn't. I'll tell you what it is. And all these materials start to form. The higher is the temperature at which a material forms, the higher is the energy inside that material, the more reactive that material becomes. This C2S, whatever that is formed at a lower temperature, is less reactive. You form something else called C3S. At a slightly higher temperature, or what is written as A-light over here, and that forms at a higher temperature, is more reactive. When you're cooling down, you have more crystals that form, and these crystals are also very highly reactive. Oh, there it is. This was the picture that was supposed to be there before. You see what the clinker looks like, and you see what the gypsum looks like. Gypsum could come in many forms. It may not necessarily look like that, but clinker is usually in the form of these nodules that are of this size, around 1 inch, a couple of centimeters in size. They may be plants. There are certain plants in India where the limestone is very soft and the clinker comes out almost powdery from there. There are some plants where they're using a lot of hard material, where the clinker comes out in particles of 5 centimeters approximately in size. So it depends on what raw materials you're using. Now, this is where the fun chemistry starts. We said we don't like chemistry, we'll invent our own chemistry. So this is what cement chemistry is. We say that, just so that the chemists don't understand us, whenever we want to say CaO, we'll call it C. Whenever we want to say SiO2, we'll call it S. Al2O3 will be called A. Fe2O3, F. there should be a bar over there, got erased in the file transfer, SO3 bar, sulfate would be S bar, water would be H. So when I talk about C2S, that's not an explosive mixture of carbon and sulfur. That is what we call dicalcium silicate, CaO twice, SiO2, and that is what is called B-lite. Because these materials are not present in a very pure form in cement. So instead of calling them by their chemical names, we give them mineral names. So they came up with names like A-lite, B-lite, C-lite, Phe-lite. That's what they used to call it, and then they thought it was too corny to have that, so they gave it some new names. And the first material, which is usually the majority of clinker, is called A-lite, that is tricalcium silicate, CaO, SiO2, and there are 3 of CaO in that, but there are other impurities along with that. Without those impurities, the crystals do not form properly. And you form specific types of crystals with a certain amount of impurities, which is why we don't write them in the chemical form all the time. These impurities could be aluminum, calcium, iron, lots of them, affecting the crystal structure. Then there is B-lite, dicalcium silicate, that I already talked about. Then there is what used to be called Phe-lite or C-lite or C3A, but this is known as tricalcium aluminate or just aluminate these days. There are 3 calciums, CaO, and 1 Al2O3 in that. And then there is ferrite, which is a solid solution of calcium aluminate, some iron in there. In that solid solution, if you put it in water, the calcium part is able to leach out of that, leaving the iron behind. We'll talk about that in a minute. But although we write those reactions in a stoichiometric way, but it's not really that what is happening. So what do you put into the cement? Here you see some examples of what the composition of cement could be. You have a certain amount of silicon in it, certain amount of aluminum, iron, and this varies a lot. Depending on whatever is available in the Earth's crust over there, depending on whatever is available to you as minerals at a certain location, you just dig that out and use that for the production of cement. And that's the beauty of cement. You can produce it using a wide variety of materials. There is no fixed formula for cement. It can have many different compositions. It can have many different properties. Now, all of these materials, so what cement plants do is they try to get a certain composition of the raw materials, put them into this kiln, that rotating tube, and try to produce a cement of a certain composition. But then the problem is, in the end, the materials don't remain in this form. They don't remain in the form of SiO2 or Al2O3 or whatever. They have to go into this form because these are the what we call phases in clinker. These are the clinker phases that are reactive, that are going to react with the water, and that are going to give you the properties of cement or concrete that you expect, right? So this is not very useful to us. What is useful to us is how much of C3S, C2S, and so on is there, which is why a certain Mr. Bogue, a long time ago, came up with these formulae. And he said that if you know the amount of calcium that's there in the cement, if you know the amount of silicon, the amount of alumina, the amount of iron, the amount of sulfate in your cement, you should be able to back calculate how much C3S, C2S, and so on is there. And the idea of making these equations is that there are these phases that have a certain composition. Let us assume they have that specific composition, and let's try to find out how much of what is present. So if I know how much iron is there, and if I assume that all the iron goes into C4AF, then I can calculate how much C4AF is present, and that's the first equation. Now I know how much iron, how much alumina has gone in this. How much Al2O3 has gone in that. I subtract that from the total alumina that is available and find out the remaining alumina, and from that I can calculate how much C3A is there, assuming that the formula of C3A is C3A, CaO, whole thrice Al2O3. Assuming that the alumina is present only in C3A and C4AF, I can find out how much C3A is available, right? Now I know how much C3A and C4AF is there. I can find out how much calcium is consumed in them. So now the remaining calcium is distributed between C3S and C2S. I know how much silicon is present. I know how much calcium is remaining for these two materials. Two unknowns, that is the quantity of C3S and C2S. Two knowns, quantity of calcium and silicon. You can easily calculate how much C3S and C2S is there. And that's what Mr. Bogue did and became eternally famous for his Bogue equations. There are many modified equations of Bogue that are also available after that. And this is what the cement industry very commonly uses to be able to calculate what the composition of the cement is. So sometimes if you go back to a cement company and say, can you tell us what the composition of your cement is, they will give you a sheet, and the numbers that are calculated in that sheet are very often calculated using the Bogue's formulae. Now, how good are those numbers? Let's try to understand that. Here I have just data dumped compositions of 4 cements that were produced in India. If you look at these 4 cements, the individual compositions in terms of SiO2, Al2O3 and so on is not different by more than 1% or even 0.5%. And yet, you use the Bogue's formula and you calculate how much alite, belite, aluminate, ferrite is present, you see a difference of 12% between them. So just by an error of 0.5% in your measurement, you can have more than 10% difference in your calculated composition of the cement. That tells you that the Bogue equations are not suitable for finding out the composition of a cement. It's very nice to understand if you've produced a good raw meal that can be put inside your cement plant to produce your clinker, but it is not very suitable to calculate how much alite, belite, whatever is present in your cement for your research purposes. For that, you may have to use another method. There are other methods. People very commonly use X-ray diffraction these days using Rietveld analysis. So Professor Srijit Krishnan is going to talk about that today afternoon. Now, something that I say about these kind of methods, Bogue analysis and also about Rietveld analysis is that when you carry out Rietveld analysis, you get a certain accuracy of calculation. There's another method which also gives you a very similar kind of accuracy. What you do is you go to a wall, you write down a few numbers. Let's say you want to find out how much alite is there in your cement. You write down 45, 46, 47, 48 until 55. You take a dart and you throw the dart at the wall. Wherever it goes and sticks, that's the composition of alite. That's almost the accuracy of Rietveld analysis if you don't do it properly. So I have seen somebody working at a cement plant calculating that they have minus 4% C4AF and just writing it down in the register, because that's also a mathematical analysis. It's a more complicated version of Bogue analysis in a way, more complicated, more technology behind it, but it's a more complicated version of that. If you use it blindly, you're going to end up with much more random numbers than you end up with the Bogue analysis. The Bogue analysis is like doing the same thing with the blindfold around your eyes and then throwing the dart. That's the accuracy that you can get with that. It's a very good method to control the raw materials that go into your cement, but not a very good method to carry out your research to find out how much of which phase is present in your cement. Now, if you look at the Indian standards, you'll find there are a lot of standards of cement that are available. I haven't even listed the 2 recent ones. This slide is very old. A lot of these cements that are listed over there, not all of them, there is super sulfated cement, high alumina cement. These are produced using other, it does have the latest ones. They are produced using other technologies, but most of the other ones that you see over there are produced using the same clinker, the Portland clinker. You blend that clinker with other things and you produce the cement. So that's how versatile this material is. There are different ways of classifying it. You can classify the cement based on what the composition is. You can classify the cement based on its performance. The ASTM standards, they classify the cements based on how they perform in terms of heat, in terms of resistance against sulfate attack. That is what they do. And that's a kind of a very rough summary of how cement is produced. Now, day after tomorrow, NCB is running a course in Ballabgarh. Not very difficult to go there. Just take the metro from here. You have to change only once. You can get down at their door. And I've already shared the links for the registration. You want to understand more about cement production, please attend that workshop. There are already like 25 people who have registered, but I think they can adjust more of you if you're interested to learn more about cement production. I can take 2 questions right now, if there are any. Did I manage to wake anybody up? No one? Good, perfect. So now I said that you've produced the cement, you've produced this material with a very high energy, and the reason why you produced a material with a very high energy is because you wanted it to be able to react with water. The reaction with water is what is known as hydration, and let's see what this hydration reaction is about. This energy that you put into the cement is released when cement is reacting with water, because everything would like to go back to a lower energy state. And when the cement goes back to a lower energy state, it releases the energy that was there inside it. And it becomes what kind of a reaction that way? Endothermic reaction? Oh, so you did study some chemistry in school, despite being civil engineers. Good. So exothermic reaction. Exothermic reaction releases heat. So one way of studying how quickly or slowly something is reacting is to measure the heat that is evolved from that reaction by keeping that material at a constant temperature. So you take the cement, you mix it with water, you maintain it at a constant temperature, and you measure the amount of heat that is evolved from that. And if you do that, you get a graph that kind of looks like this. This scale is in hours, this scale is in milliwatt per gram. The numbers are not there deliberately. I'll tell you why. But what it looks like is that cement is not really able to make up its mind. You mix it with water, it reacts for a little bit, there's a lot of heat that is released. And after releasing that heat, it says, I'm tired, that was hard work, let's go back to sleep. So here you have what is called as stage 1, or what a lot of people call the dissolution stage. And then you have the second stage after that, where the cement is tired, it's sleeping, where people call it the dormant stage. I don't like the term dormant stage, because dormant means something is really sleeping, but we usually measure a small amount of heat. So we call it the induction period instead. Sounds more fancy, more sophisticated instead of dormant. That's why we call it induction. So you have an induction period where there's a certain small amount of heat. So the cement is tired, it's resting for a bit, it's doing something, but not nothing. And then it says, yeah, I've got the energy now, let's start to react again. It starts to react again, and then it gets tired once again, and it starts to sleep once again, but then it says, okay, let's try once more. Gives another push, but then it says, no, I can't do it. And then it goes back again, and then it slowly continues to react over time. There are certain cements, for example, if you take, you've heard about self-leveling screeds, where you take a bucket of a screed and you pour it over a floor, it'll make a perfectly flat horizontal floor without doing anything. Those screeds are made using very complex compositions. Those cements wake up after 1 day, after 2 days, and they say, okay, I want to react a little bit more. And then they go and sleep once again after that. So it can be much more complex than this. This is just the Portland cement clinker. The reason why you've got all of these things happening at the same time is something that the scientists have been arguing about for a long time, because if scientists don't argue, there's no other way to justify our jobs. So the day we stop arguing as scientists, we are essentially saying that there's nothing to argue about, everything is known and understood perfectly, so we will not be able to justify why we are getting our salary, so we have to argue. So because of those arguments, we are not 100% sure why these things are happening, but still there are certain assumptions behind it. People think the first stage is about dissolution. The dissolution happens very quickly. For the second stage, some people used to say that there is a layer of a product that forms around the cement particles. They're not able to dissolve anymore, but nobody is able to see that layer in any microscope, in anything. So that hypothesis is almost not accepted by anybody these days. What they say is this is the stage where the reaction is getting set up, where the nuclei for the reaction are getting set up. And then as those nuclei grow, the reaction becomes faster and faster because there is more surface available for reaction, in a similar way as solidification happens in steel. Steel is where people got this idea from. And then it starts to slow down because the material starts to become more solid. And we'll talk about those things afterwards. But an important reason why you get these ups and downs is because there's no single thing reacting inside the cement. There are so many different phases reacting at the same time. Everything dissolves together at the same time. They go into the same water. Now your cement in the beginning is like a dispersion of particles. It's like a solution. You put the cement in, things dissolve, the materials go into the solution, the ions go into the solution. The ions from C3S, from C2S, from C3A, everything, the gypsum that you've added, they go into the solution, they keep colliding with each other and do whatever reaction that they can with the other material, and which is why you end up with such a messy system, because all of those things are trying to react at the same time. And something reacts faster, something reacts slower, something happens first, something happens later, and that's why you get these bumps. What is it that happens first? One of the first things that happens is the reaction of aluminate, C3A. And this is something that we worry about. This is something where I usually invoke my friend who's called Ramu. Now, Ramu is the guy who you've seen working on the roadside with cement. Have you seen him? Have you seen Ramu? Anybody who hasn't met Ramu? Anybody who's called Ramu over here? No, there is there's no insult that is meant by this. But Ramu is that guy you've seen working very hard on the roadside with cement, concrete, plaster, whatever. Now this guy would like to be able to mix his cement with water, with sand, whatever it is that they're producing. And it's not just Ramu, it's Ramu, his wife, his entire family who's involved in the business. So they're all working together and they're producing this cement. And the moment they mix this cement, they find that it becomes very hard, it becomes impossible to apply it anywhere, it becomes impossible to use it anywhere. And Ramu gets very upset because he said, I don't like this brand of cement, I'm going to buy the other one. I'm not buying the one that Amitabh Bachchan is endorsing, I'll buy the one that Rohit Sharma is endorsing. This is what Ramu would say. And because maybe the one that Rohit Sharma is endorsing is the cement that gives Ramu more time to work with the cement so that he can at his own pace properly apply the plaster or mix the concrete or whatever it is that he is doing. So what used to happen in cement, or if you just take clinker and mix it with water, what would happen is that the C3A in the cement would react very rapidly with water and produce hydrogarnet. And when this reaction happens, it's so rapid, it does not give you any time to work with the cement. And what happens if you don't have time to work with the cement? Ramu is upset. Come on, don't underestimate the value of Ramu here. That guy is upset. If that guy is upset, nothing will get done. So he's upset. He wants to have a certain amount of time for the cement to be able to work with the cement. So what they did was they mixed gypsum in the cement. Remember, we were grinding gypsum along with the cement? The reason why we are grinding gypsum with the cement is gypsum is ultra active. It dissolves very quickly, even faster than C3A. It goes into the solution, produces sulfate ions. These sulfate ions force the alumina to react with the sulfate. People say that some of the sulfate goes and absorbs on the surface of the cement particles, slows down their dissolution. I'm not 100% sure because, once again, there's something for which we don't have any evidence. That's something we'll continue arguing about to justify our jobs. But when C3A finally does start to dissolve, it finds gypsum in the solution. Sorry, this should be S bar once again. I don't know where the bars went, but this should be S bar. So it reacts with the gypsum, produces something known as ettringite over here. This should be S bar. That is calcium aluminosulfate. It's also known as the AFT phase. This ettringite produces needles, but the important thing is its reaction is slower. It's still a very rapid reaction, one of the first reactions that happens in cement. But then this reaction is slower than the production of hydrogarnet over there. Eventually, when the gypsum runs out, the more of C3A will react with some of the ettringite, again, and S bar over there. So there should be a bar. Okay, I'm not able to do that. A bar over there, a bar over here, a bar over. You get the idea, right? Okay. So that's how it should be. Above the S's, there should be a bar. But that's what we're calling the sulfate. Some people use the dollar sign. I should start doing that because the bar disappears apparently. Now, when the gypsum runs out, the C3A will react with the ettringite to produce something else known as the monosulfate, monosulfoaluminate. This is calcium sulfoaluminate. This contains 3 sulfates over there, and this is called ettringite. And this one contains a single sulfate over there. This is calcium monosulfoaluminate. All right. Now these reactions are slower than the reactions of than the first reaction where hydrogarnet is produced, but the important thing is you have to have the right ratio between gypsum and alumina. If you have too little alumina, if you have too high an alumina and very little gypsum, you don't put enough gypsum, the cement will still set quite quickly. And what will happen? Ramu will be unhappy. Yes, exactly. Now you understand whole of cement chemistry. It's all about that guy. So, if you add a little bit more of sulfate, what will happen is you'll get a good, long working period with the cement or concrete. It will not set for some time. Setting means that you've got these cement particles that are stuck to each other because of some product in between them, something holding them together. And what is holding them together is this product. It could be ettringite, it could be hydrogarnet. So when the cement is set, and if you try to move the cement, work with the cement, what happens? Let's say there's a crystal joining two cement particles together. And now it is becoming hard and stiff. You move these cement particles, you break the crystal of whatever was formed in between them. You break the crystal, you are breaking bonds that were formed as a result of the energy that you had put into the cement at the time of its production. Once you break those crystals, you're losing the utility of the energy that you put in at the time of production of the cement. You will permanently lose strength in the cement or concrete if you manipulate your cement or concrete after setting has taken place. If you have high amount of alumina, you need to put more gypsum. If you have less amount of alumina, you need to put less gypsum in it. If you put too much gypsum, even when you have less alumina, what ends up happening is some of the gypsum may precipitate. This also happens if you've got what is called hemihydrate or anhydrite in your cement. You know what gypsum is? Gypsum contains two water. It's calcium sulfate, 2H2O, right? So now when you're grinding the cement, it gets very hot in the mill. If it's very hot in the mill, this calcium sulfate is going to decompose, is going to get dehydrated and produce calcium sulfate hemihydrate, half H2O. And the moment you mix it with water, it's going to react a bit and it's going to start producing gypsum or 2H2O and precipitate as crystals of gypsum. That may also give you what is known as a false set. If you have too much of gypsum, what may also happen is when you're mixing the concrete, the gypsum will dissolve in the water. The moment you stop mixing, the gypsum precipitates and it creates crystals, and these crystals hold the cement together. So the thing holding the cement particles together is not a product of hydration, it's the precipitate of gypsum or sulfate, and that leads to a pseudo or what is known as a false set. If you mix your concrete once again, you do not lose any energy that you had put into the cement at the time of production. You can reuse your cement, but then again, Ramu will be unhappy. So you don't want to do that either. All right, so it's very important to have the right amount of sulfate and depending on the amount of alumina. Most people, one quick simple way of checking if you've put the right amount of sulfate in your cement is to carry out this test that is known as the isothermal calorimetry test. When you carry out this test, you see the second hump, you should see a proper peak that appears like this, and you should see a second hump, which is a sharper hump, appear after the softer peak. And if that happens, you put the right amount of gypsum. The most common way of measuring it in cement plants used to be to optimize the one-day strength of the cement. By optimizing the one-day strength, you're able to ensure that you've put the right amount of gypsum. Now, since we were talking about the alumina reaction, let's also get done with this. The ferrite. Ferrite is a very slowly reacting phase. It's not a quickly reacting phase, but like I said, it's a solid solution. Although I've written some stoichiometric reactions over there. I don't know if I can erase those bars now. Maybe. So those bars are still needed, but I hope you understand where to put them. So ferrite is ferrite contains calcium aluminate, it contains iron. This iron usually stays behind at the location where the particle was and reacts very slowly. The calcium aluminate part can react more quickly, but still, it's a slow reaction. The products produced are similar. It can produce ettringite, it can produce monosulfate. It contains an excess of calcium, so it will also produce calcium hydroxide. The hydration product of calcium oxide is calcium hydroxide, right? So it will also produce calcium hydroxide, which may do other things. The iron will eventually go to a hydrate form. Ferric hydrate eventually, but that reaction is going to be very slow. But let's come to the more important reactions. The reaction of the silicates. The silicates make the bulk of the cement. In most of the cements, you would find that the largest components are C3S and C2S. In Indian cements, the typical amount of C3S is 45 to 55%. You go to Europe or US, it's more like 60 to 70%. Some countries, it could even be higher than that. It depends on the composition of the raw material that you have. It depends on how you've produced the cement, how much time did it have inside the kiln, how much fuel you decided to put into it, a lot of things, operational parameters as well. So C3S and C2S make the bulk. In Indian cements, C2S is around 25%. Go to Europe, it's more around, it could be around 10%, 15%. So our cements are generally higher in B-light, lower in A-light. Okay, that's also fine. Higher in A-light. Our cements are usually lower in B-light, higher in A-light. And, but then what's more important is the reactions that are happening. So both of these phases, C3S and C2S, they have a similar kind of a reaction. They react with water to produce what is called calcium silicate hydrate, or CSH. And along with that, it produces calcium hydroxide. Now the CSH that I've written over there, I have dashes in between. I have those numbers 1.7 and 4 over there. This is C3S and C2S react with water to produce this calcium silicate hydrate, and what I've written over there are some numbers over there. These numbers are not very sacrosanct. These numbers are not very well defined. What CSH is, the calcium silicate hydrate, this contains sheets of calcium silicate. Of course, that's another thing that the cement chemists, the researchers, they all argue about what CSH is made of. Maybe the people who talk after me are going to tell you about a completely different structure of CSH. Will you, Aslam, tell us that CSH does not look like that? It does look like that? Okay, he believes me now. So this model that I'm showing you is actually from, there are these sheets of calcium silicate hydrate, calcium silicate, sorry. They are these sheets of calcium silicate. And these are like, some people call them needles. I don't believe they're needles. They have to be sheets. These are sheets. These sheets are either densely packed or loosely packed. Depending on how well they're packed, the space in between them is filled with water. That's why it's a hydrate. And there are 3 types of water on that. There is one type of water that is there closely in between these sheets that is holding these sheets together. There is a water that is attached on the surface of those sheets. That is called the surface water over there. Here, this is the interlayer water. And then there is water trapped between these. These sheets are just growing randomly, like foils at different places. And you've got empty voids over there where small pockets of water are trapped. All right? Now, this water is what is giving you strength. But how can water give you strength? Can water give us strength? Any of you played with a water balloon? A water balloon. कभी तो बचपन रहा होगा, नहीं रहा आप लोगों का. रंग डाल के खेला है ना? तो if what you do is, I'm sorry, I hope all of you follow, almost all of you, I know Hans doesn't, but follow a bit of Hindi already, Hans? All right. So, if you take a balloon and you take some water, you throw the balloon at some person, at the same time throw some water at that person. Will it have the same effect as a water balloon? No? You have to fill that water inside that balloon and throw it at that person, and then it has the desired effect. Right? That's when it's most fun. But why is that? The balloon itself will not hurt you so much, the water will not hurt you so much, but the water inside the balloon will hurt you. Because the water is inside a confined space. If the water is trapped inside a confined space, it will also have mechanical properties that are different from the mechanical properties of just the balloon or just the water. And now you get this water trapped inside the space, which gives you a certain hardness. But even better, let me take you back to your childhood once again. I don't know what happens now, but in our times, we did not have waterproof bags to carry our notebooks to school. So whenever it rained, You arrive at school, the notebook would get wet, and you would have a lot of difficulty separating the sheets of paper. That happened, right? I don't know what generation is going on right now, Z, Alpha, Beta. I don't know if Alpha, Beta generation has witnessed that, but we did. But what got added in between those sheets? Water. Is water a glue? Yes, in this case it is, because the water is holding the sheets of paper together. Why is it holding those sheets of paper together? There are bonds, hydrogen bonds, for example, that hold. Hydrogen bonds can be very strong. Do you know of something big that hydrogen bonds have done? Something really big. It sunk the Titanic, right? It was a glacier. It was hydrogen bonds that actually led to the sinking of Titanic. It was not those two people who were, I don't know, changing, I don't know what, but it was not about that. I know you've heard about Titanic only from the movie. But the hydrogen bonds can be very strong. It's these hydrogen bonds. It's those simple bonds that are holding these sheets together. This building that you're sitting in is held together by water. It is this water that is an important part of the cement. That's why we call it hydration. This is the water that is holding everything together. This is the water that is giving your concrete the strength. This is the water that is needed in your concrete. The water is required in your concrete to get the strength, to get the performance that you want. It's not just in this calcium silicate hydrate, where it is present in these three forms. It's also present in other materials like calcium hydroxide. The other products that you see, ettringite, had 32 molecules of water. Monosulfate had 12 molecules of water. All of these crystals have what is called bound water, a water that has solidified and given you something that is strong. Just like a piece of ice that you tried to chew and broke your tooth. Done that? Not had childhood? No, I guess not. But it can be very strong. So if you think that water is not important for cement, cement is the strong part, water is not needed, or water is not giving the strength, you're wrong. Water is what is giving the strength in all of this. So it produces the CSH. CSH is a material that changes quite a lot. It's very adjusting. Depending on how much space is available, these sheets will spread out more or less. Depending on that, there will be less space inside or more space inside, more water inside or less water inside, whatever. Depending on how much calcium is present, there may be less or more calcium in these sheets. Depending on other things that are present, aluminium, magnesium, whatever, all of that. This is one of those friends that says, "Acha, tumhe bhi chalna hai? Aa jao. You also want to go with us? Come on, join us." It's one of those friends, this calcium silicate sheets. It just adds whatever comes over there. It adjusts to whatever is available and produces a material that is highly adaptable, that changes based on the composition of cement. Whatever is inside your cement, be it your plain Portland cement, be it your blended cement, and it fills in water. So these numbers, 1.74, they have no meaning. This 1.7 could be 1.2, it could be 2.0, this 4 could be 2.5, it could be 6, depending on how much of water is available inside the cement. And so it's a highly variable material. I'll not go through this, but people have tried to understand what this calcium silicate hydrate looks for so long. People gave it different names. So calcium silicate hydrate has been like the religion of cement. When there is a God that you believe in, you give it 10 different names. That's what 10 different names have been given to CSH. You've got people, Powers was one of the people who studied it at first, 1940s, 1950s. He just called it the gel. He said all the product is gel. Hey, gel? What's the meaning of gel? Gel also means bind, which is what cement does. Gel gives you a feeling of something that has water inside it. So Powers called it gel. People started calling it tobermorite gel. Some people came in between and they said, no, tobermorite is not accurate. Genite gel. But then others came back and said, no, you're wrong. It's not genite gel, it's tobermorite gel. People kept changing all of those things, but they tried to look at it using microscopes. One of the first specimens that was studied using a transmission electron microscope was a cement sample. When I tell people that I work on cement, a lot of people laugh at it. Do you also have that kind of experience? They say, cement? Is cement something to work on? Is it something really worth studying? But it's a very complex material. You can understand that by the fact that one of the first specimens to be studied using electron microscopy was a cement sample, and this is one of the older images. This is not the first image, of course, but this is one of the older images where what people saw was these cement particles with these fibers coming out. In this image, the dark part is the solid. There were later images. Here also the dark part is the solid. This is a much later image using transmission electron microscope, where you see you have these fibers kind of coming out from that solid. It looks like fibers because you're looking at it in 2 dimensions. If you look at a sheet in any other dimension other than from the top, it'll look like a fiber if you just cut through a section of that. So these are sheets over there. So here you see a relatively more recent image from a friend of mine where the bright part is the solid in this image. This is called a dark field image. In this image, what you see is this is the cement particle. The denser part, the cement particle, probably the original boundary of the cement particle was somewhere over there where something has deposited, and then the cement particle is dissolving in water. It's becoming smaller. As it becomes smaller, there is something depositing in between that space where the original boundary was and the space that is left behind by the dissolving cement particle. And this is what we call an inner product. These are just some images that show what the microstructure is looking like. Another image from another friend of mine, where you see within 10 hours of hydration, you see between all of these, this is a cement particle, this is a cement particle, there is the CSH growing everywhere, almost everywhere. It grows almost everywhere inside the microstructure, tries to occupy all the space that it can, but there are also crystals of other materials that are produced. Now, I know a lot of people get disappointed sometimes when we read papers in cement and concrete research or cement and concrete composites. There are people who, without doing an NMR, would not believe any result. You absolutely have to do an NMR for your result to be scientific at all. But some of the best researchers, greatest, most well-known researchers worked without those techniques. Powers gave his ideas about the cement microstructure back in 1940s, 50s. At a time where he did not really have an access to a microscope, he used to go to another lab just to see some images for fun. And he gave this model of what the microstructure looks like at a time where all the things that he could measure were compressive strength, temperature, length change, weight change. Those kind of things you could do with basic equipment. You don't need very complex equipment for that. And he came up with some very accurate models that still hold today. So what Powers said was, in the microstructure, you've got this gel. This gel contains a certain amount of water. He said 22%. Like I said, it could be a little bit different, but it's not very different from what Powers proposed. He said wherever the product has not been able to reach is called a capillary pore. The rest of the place is the gel. Inside the gel, there is also some water. That's called the gel water. That's what Powers said. And what he said was that the volume of the gel is 2.1 to 2.2 times the volume of the solid that had reacted. That is what he said a long time ago. There were others as well around the same time. Again, Feldman and Serida, what they measured were length change, weight change, and they came up with this model of CSH. And they said inside that gel, this water is present adsorbed on the surface of the calcium silicate sheets, between those sheets, holding those sheets together. In the pockets left behind between these sheets, there's water trapped inside like that water balloon. And all of this is contributing to the mechanical properties of the concrete, to all the other properties of the concrete. And all of these people worked with techniques that were very simple. There are other products as well. Calcium silicate hydrate is not the only product, although it's a very important product. One of the other products produced from the hydration of silicates is calcium hydroxide. Because you remember, silicates were C3S or C2S. For every silicon, you only need like 1.2 to 2 calcium to produce a calcium silicate hydrate. So the remaining calcium goes to produce calcium hydroxide. People say that calcium hydroxide is a very bad product. I've read some books where people say that calcium hydroxide is a bad hydration product. It's not. It's a wonderful hydration product. It binds, it gives you strength, it's a good crystal, it has no porosity, no permeability, it doesn't allow anything to pass through it. It buffers the high alkalinity inside cements. You know, when I showed you the composition of cement, something we skipped over was that they also contain sodium and potassium. The sodium and potassium maintain a high pH inside cement, above 12. 13 of that range. And this calcium hydroxide is buffering that solution, is making sure that you're maintaining a high pH, and that protects the steel inside the concrete. We're able to make reinforced concrete because of that. It's an excellent product. This is a material that usually forms bulky crystals, but it depends a lot on what's present inside the pore solution. It is also very useful for producing blended cements that Professor Piyush Chonsali will talk about afterwards. The ettringite, the monosulfide, where did the ettringite go? Yeah, ettringite. The ettringite that is produced has needle-like crystals. Now, these needle-like crystals, when they're growing in the beginning, see, now, my friend Aslam is sitting over there. Let's say he was very close to me. If I produced a needle like this and this needle would grow from here to him, that needle would be pushing him away. And the growth of ettringite can cause expansion because of that. It can push the particles away. It can lead to expansion. But in the beginning, when cement starts to hydrate, there's plenty of water. There's plenty of space around. So the ettringite can easily grow without having to push anything away. But then, if this ettringite forms in the long term, it can lead to expansion, it can lead to cracking. But in the beginning, this ettringite forms needles that do not lead to cracking, that do not lead to expansion, because there's plenty of space for these crystals to grow. And eventually, in Portland cement, I'm putting that caveat over here because it's more complicated than that, but eventually in Portland cement, when gypsum runs out, this ettringite is going to get converted into monosulfate. Please put the bars again wherever they're needed. It gets converted into monosulfate, and the monosulfate has more bulky crystals, is not needle-like, and does not lead to those kind of reactions. So all of these reactions that are happening are exothermic reactions. There are some numbers over there. Don't need you to remember that, but that is why we are able to measure it using isothermal calorimetry. So while those reactions are happening, all of those materials are reacting almost at the same time. But different materials have different rates. Different phases have different rates of reactions. Like I said, aluminate reacts the fastest. So if you measure how much of aluminate has reacted, you'll find it has reacted the fastest. After that comes alite. Alite is slightly slower than aluminate in how much of it reacts, at what rate. And then slowly over time, C2S and ferrite also start to react. There is a kind of controversy on which reacts faster. It depends on the system. But both of them are reacting almost at the same time, usually in the long term. Have you heard of the common ion effect? You know what the common ion effect is? If you've got a solution in which, let's say I put calcium carbonate and in water, calcium carbonate would dissolve in the water? Yes, it does. Slowly, but it does. If along with that calcium carbonate, I put some calcium hydroxide in water as well, would the calcium carbonate be able to dissolve? Not much, because calcium hydroxide would dissolve faster. It would saturate the solution with respect to the calcium and not allow the calcium carbonate to dissolve. So that's a common ion effect, right? Maybe I'm not very accurate, I apologize to the guests, but that's what we do in cement. We're talking to people who barely passed chemistry, but that's the idea. If the solution gets saturated rather quickly, other things would not be able to dissolve very quickly. You've got calcium in each of those phases. If one of those phases dissolves very quickly, like C3A, it increases the concentration of calcium in the solution, prevents the other calcium-bearing phases from dissolving. C2S, ferrite, even alite dissolution slows down if aluminate dissolves very quickly, because the calcium goes into the solution already because of that. So now, because one thing is dissolving, the other can't. So as long as C3S is dissolving rapidly, there's plenty of C3S and it can dissolve, C2S has no chance. It has the same ions. It produces the same ions as the dissolution of C3S. So as long as C3S is dissolving, C2S cannot dissolve because the solution is already concentrated or has a high concentration with respect to the calcium ions and the silicate ions. So it cannot dissolve as quickly. The dissolution slows down. Once your aluminate and alite hydration slow down, there's very little C3S and C3A left. Only then the other two phases can really start to dissolve and react properly. And that's why they react later, because they have these common ions in them. So the rates of reactions all of these things are different. That's why some people say that C3A and C3S contribute to the early strength and C2S contributes to the long-term strength of concrete. Yes, it's partially true, but everything is reacting all the time. Everything is contributing to all the ages. But yes, it is true that if you have more B-light present, you'll have a higher strength increase over the longer term than in the early age. Now, while all of these materials are reacting, what happens is these products are being produced at the same time. Calcium hydroxide gets produced, calcium silicate hydrate gets produced, yttrium hydrate gets produced. But the important thing over there is that the volume of these products that are produced from the reaction is more than the volume of the reactants that were reacting. If halite reacted to produce CSH and CH, the volume of CSH and CH is more than the volume of the halite that reacted. So you end up having more solid. Where is that volume coming from? Why is the volume increasing? The water. The water is getting incorporated into the solids. The water is giving you the solids, and the water is also contributing to the solid part. So a liquid that you added to the concrete at the beginning, which was water, to make the concrete workable so that you can give it whatever shape you want, that liquid is now becoming a solid and is now contributing to the properties of the concrete. Right? The solid volume increases. I'll show you some numbers in a couple of slides. And because of that, these particles start to stick together because there is more solid and less liquid as hydration happens. One more thing that's happening along with that is, although the solid volume is increasing, so unhydrated cement had this much volume. When it's fully hydrated, that's the volume of the hydration products that are formed. So the volume of the solids has increased, but if you take the total volume of water and the cement put together, you see that the total volume reduces and you create some voids inside it. This is what is known as chemical shrinkage. Okay. Some people also call it Le Chatelier contraction. Have you heard of, maybe you've heard of Le Chatelier contraction? People saying that, have you heard that term? Le Chatelier apparatus, heard of that? Okay, first tip, don't call it Le Chatelier, please. It's Le Chatelier. Please pronounce with me. Le Chatelier, right. That's the pronunciation. There's also another one. There's an apparatus that you use for setting time. What is that called? I heard Vicat, I heard Vicat. What else? Vica. The T is silent. French people do that. The T is silent. Vica apparatus. All right? The Vica test. So very important when you're presenting at an international stage. You would like people to be able to understand you. So that's Le Chatelier from now on and Vica from now on, right? So Le Chatelier contraction. This is what Le Chatelier contraction is about. And let me tell you what happens over there. So let me show you this reaction and show you some numbers along with that reaction. This is the reaction of C3S reacting with water to produce CSH and calcium hydroxide. CSH is calcium silicate hydrate once again. If I list down the densities of those materials or the specific gravity in gram per centimeter cube, it's 3.15 approximately for C3S. What is it for water? 1 at a certain temperature. CSH is around 2. Calcium silicate calcium hydroxide is around 2.24. All right. Now, if I find out their molecular masses, CaO whole thrice plus SiO2, if I added all the molecular masses, it comes to 228. 18 for water, calcium hydroxide is 74, CSH comes to, if I assume the composition of CSH is C1.7 SH4, then this comes to 227.2. All right, this is what it comes to. So I had shown you this reaction earlier. To balance this reaction, I had to have 5.3 water and 1.3 of calcium hydroxide was produced. All right, this is what I needed to do to be able to balance this reaction. So let's come back over there. We have these numbers 5.3 and 1.3 over here, and now I calculate what is the mass that is reacting. So I multiply this number by that number, 228 grams. The mole concept. 228 grams of C3S reacts with 95.4 grams of water to produce 227.2 grams of CSH and 96.2 grams of calcium hydroxide. All right, I divided by the density to find out their volumes. This is the volume of C3S that reacts. This is the volume of water that reacts. The volume of CSH that is produced. The volume of calcium hydroxide that is produced. All right, simple calculation, basic arithmetic, not even algebra. All right. Now I find the ratio of all of these volumes to this number over there. This is 1, this is 1.318, 1.567, 1.590. All right, those are the numbers. Let's see what we get from that. The first thing that we see is, if we add these two up, we get 2.163 over there. Of course, it's not that accurate. I shouldn't write to the third decimal place. But you had 1 unit volume of solid to start with. You ended up with 2.16 unit volumes of solid after the heat. The volume of the products is more than twice the volume of the reactors. And that is what fills the space. And that is what gives you the strengthening. The other thing that you would notice is this plus this is 2.318, but this one is 2.16. Right? That means the volume of solid plus liquid is reducing after the reaction. And because the volume of solid plus liquid is reducing after the reaction, you produce voids inside the cement paste. Because now, if the cement paste has set, the size of the box in which the cement paste is cast is set. And since the size of the box is set, you will have to produce voids inside to compensate for the space. Hi. Hello. I can hear you. So, the size of because the size of the box is set, the reduction in the volume manifests in the form of these voids that are produced inside the cement paste. This is what is known as chemical shrinkage or Le Chatelier contraction. Now let's see some more things from these numbers over here. One more thing that you would notice is that if you find out the ratio of this weight of water to the weight of C3S, can you find out what that ratio is? Divide 95.4 by 228. You will get 0.42. All right? At a water binder ratio of around 0.42, you have just enough water to react with all the cement. You have just enough cement to react with all the water. You are at a stoichiometric balance for this reaction. There are other reactions as well. There is the reaction of C2S, there is the reaction of aluminate and all of it, but those numbers are also very similar. For an overall cement, for the reactive part, this number varies between 0.4 to 0.45 if you calculate that. So, at a water binder ratio of around 0.42, you have just enough water to react with all the cement, just enough cement to react with all the water. Theoretically, not practically, theoretically all the cement can react with all the water. There should be no unhydrated cement left. There should be no water left. If you have a water to binder ratio higher than that, if you have a water to binder ratio, this is the perfect water binder ratio. Can you see that? All the cement is consumed, all the water is consumed. If you had a water to binder ratio that was higher than that, you had less cement, you had more water, you would have water left behind and no cement left. You would have more pores left behind because of that. Pore is everything that has water and is empty inside the concrete. If you have more pores left behind, you end up with something weaker. Also more porous, more permeable, allows anything to come in from outside, less durable as well. All right, that's why higher water cement ratio is bad. If you made a concrete with a high water binder ratio, let's say 0.5 water binder ratio, and you say that's fine, I put less cement in it, but I'll cure my concrete perfectly. Any use of curing it afterwards? Keep putting water from outside. There's no cement left. There's no point curing it. As long as you prevented the water from evaporating, that's fine if you had a high water binder ratio. And that's fine because that will let you hydrate all the cement that's there, but you will not get to a very high strength. Whereas if you have a lower water binder ratio, you have more cement, even after all the water is finished, you end up leaving some cement behind. In this case, when you have a lower water binder ratio, you started with more solids, you end up with more solids, end up with less pores, get a higher strength, get a lower porosity, get lower permeability, better durability as well. In this case, there are some voids left inside the concrete. If I cure my concrete, put water from outside to fill these voids, maybe that water can react with that cement that's left behind, maybe. And if it does that, it will also fill some of those voids. The concrete will become even stronger. There is some use of curing over there. But what if I just seal it? I just spray a curing membrane on this concrete with a low water binder ratio. Will that help in curing the concrete? There's no water left. The water is consumed. In low water binder ratios, I need to provide more water from outside afterwards to continue the hydration, to continue filling the voids. And it's just the opposite that we do. Usually, I don't know if some of you are coming from site practice, where do we use the curing membranes? On columns, which have the higher strength concrete. They have the lower water binder ratio. They need more water. They need more wet curing. And what we do is we seal the concrete. Yes, sealing the concrete is good. It prevents evaporation, but it will not give you the extra water that is required for hydration, right? So what happens? So Professor Srijit Krishnan will talk more about microstructure. You talk about microstructure development afterwards, right? A little bit. But what happens is, I'll draw it very simply. I have this very nice equipment in the lab with which everything looks spherical, and I can see these very nice microscopic images. Cement particles appear red, products appear to be green and blue. And you see as cement hydrates, the red part, which was the cement particles, becomes smaller, keeps getting smaller because it's dissolving, going into the solution. There is less of red left at the end. There is more of the blue and the green, which are the products, let's say the CSH and CH, that is produced. They deposit at various places inside the microstructure, hold these particles together, reduce the pores, reduce the empty spaces in between, hold all of these particles together, not just hold the cement particles together, but hold the aggregate particles together, the sand particles together, giving the concrete the strength. And this is how microstructure develops. You look at it over time in a microscope, you've got these products growing inside the microstructure, keeps filling the spaces. The products start growing from the particles of the cement. They start filling the space in these, you can see them in this micrographs. In these micrographs, at one day you have more product. The brighter materials in these microscopic images are the solids. The black part is the pore. You see there is less pore compared to this one at 12 hours. Even less pores go down to 28 days. You end up with a paste, a matrix that contains a lot of solids, very few pores, everything properly bound together. And ladies and gentlemen, that's how hydration happens. Thank you.